Moving on to the next speaker under the topic of telemanagement of very small in vivo devices, we have Dr. Robert Sclabassi. Dr. Sclabassi has been working in the field of neurological stimulation devices and studies for many years, has been advising the National Science Foundation and other national bodies in this area. And we're pleased to have an accomplished inventor with many patents to your credit here to help us take the next step in understanding about telemanagement of very small in vivo devices with a focus now on the in vivo devices into the brain. Again, an area which our keynote speaker, Dr. Ray Kurzweil, has written extensively and projected that this will be a leading area in the next couple decades of medicine. Please join me in welcoming Dr. Sclabassi, speaking on the topic of brain implantable computing platforms.
Good morning. I first of all would like to both thank and congratulate Dr. Rothblatt and United Therapeutics for organizing and sponsoring what promises to be a very exciting conference. I'm very excited about the next 2 days and know I will leave here with many new ideas. What I'd like to talk about this morning is the brain implantable computing platform, and this represents the work of a team of about 20 people. And the work has been going on, focused on this particular issue for about a year at this point, and we envision it as going on for multiple years. So what's the motivation behind this? Well, there's a convergence of developing technology. First of all, our understanding of the neurosciences has really very rapidly escalated over the last 20 to 30 years. Both in terms of basic neuroscience and clinical neuroscience. And there's at the same time a very rapid change in the availability of micro and nano electronics, which is in itself promising to continue to escalate at an extremely rapid pace over the next 2 decades. So our feeling was that now is the time to try to put these divergent fields together into a very meaningful way. So that's the motivation behind this work. And there's many disease states out there at the current time which could benefit from this. And some of the things which are most obviously fall into that category are intractable epilepsy or movement disorders, things which are currently already being treated. So the question was, how could you develop a brain implantable computing platform that could support this? So what we envision in this case is a device, a computational device, which would be distributed. First of all, there would be multiple implantable devices in the brain, which would be on the scale of a millimeter, cubic millimeter volume, so extremely small. And actually, if you project out 40 years, would probably be far less than a millimeter for an implanted device. That would use less than a milliwatt of power. So essentially a full computational engine implanted at various sites throughout the brain, which would have communication capabilities between these devices, namely they're distributed, and they would be able to do computations on measured data and drive therapeutic devices and also communicate outside of the brain. So that's the vision of the device. And so the goal is to develop this technology, realizing, of course, that we're looking multiple years into the future. I probably will not see the conclusion of the project, but I hopefully will see some of the good parts of the project. So that's the vision. So what are the requirements? First of all, the concept is a customizable distributed computational architecture based on nanoelectronics, and we'll spend some time talking about that. It has to be extremely energy efficient. It has to fit into a severely constrained power envelope. So totally implanted. Our good friends from Medtronic wasn't touched on, but Medtronic makes a deep brain stimulator. The joke in the neurosurgical circles is the most expensive battery change in the world is changing the battery on a DBS stimulator. So we want to get away from that. So we want sustainable wire-free delivery of milliwatt level power. We'll talk about a couple of approaches we're investigating to that. It has to have minimal thermal interference to surrounding tissues. Namely, you're going to be using power. This power is going to radiate into the surrounding tissues. Obviously, brain tissue is very sensitive to temperature changes. If the temperature environment in the brain changes by a degree over an extended period of time, you can induce significant damage to brain tissue. So this becomes a very significant constraint on the development of a device of this type. Efficient wireless communication. This is extremely important. Things that people have used so far today will not work in the conceptualization of this device. So, and we'll talk about some approaches to that. Novel sensors to interface with brain tissue. This is one of the reasons why this conference is so exciting to me. This is the biggest problem that we see is what kinds of sensors can you use over the long term, and probably the solutions are going to lie in the areas of the nanocarbon tubes of some type. The cubic millimeter form factor, as I discussed, that's important because you're going to be implanting these devices distributed within the brain with biocompatible packaging. What does that mean? You can't get glial reactions to the devices. You can't have the devices leaking metallic ions into the brain tissue. You know, all the innumerable things we can think about. And secure and reliable operation over a multi-year time frame. You don't want to have to crack someone's skull every 2 years to change the battery. So these are the constraints. This is what we're trying to work within. This just gives you kind of a comedic version of the device. And this would be an example of an implanted device. So this would be a cubic millimeter package. Currently we have these flexible arms sticking out, which you could envision as a disc surrounding the device, which would have implanted in it, in this particular version, some electrodes, some coils for both communication or transmitting, receiving or communicating information or energy, some other kinds of recording devices. And then there'd be multiple of these small devices implanted within the brain. There'd be some therapeutic device integrated with them, and there'd be the distribution of information between these devices. And in this particular schematic, we had some wires in there, but we really envisioned this whole thing working without wires. And we have an RF coil here, which is one of the things we intend to do away with, and we'll talk a little bit about this. And we represent the idea of transmitting information outside. This particular schematic was for dealing with this problem of intractable epilepsy. A large number of epileptic patients, a significant number, are not treatable by either medication or surgery, but there is a lot of data developing that shows that by stimulating the anterior thalamic nucleus, you can suppress seizure activity. So if you could do that for these people, today they can't work, they can't drive, they really can't do anything. So it's a big advance in terms of their lives. So anyway, that's the conceptual approach that we're talking about. The basic major subsystems, I think, are kind of there without having to talk a great deal about them. There's the computational engine, there's the wireless communication, there's the power, the application-specific signal processing, and the data acquisition. These are the things which have to be built into this package and which we're focused on at this point attempting to develop. This diagram is busy and it'll be on the website, so I'm not going to go through it in great detail. I think I want to just call your attention to the bottom row here, and this kind of lays out what we see as the requirements on the system in the next 5 to 10 years. And we're talking about power on the order of 1 to 2 milliwatts, 400 to 100 channels of data being recorded within a single one of these chips, sampling rates on the order of kilosamples per second, processing power on the order of 3.2 million operations per second, storage on the order of a gigabit, basically, of storage, wireless communication, and wire-free permanent energy being applied to the system. So this diagram in general is worth looking at in its totality, but as I say, it's a little bit too much to assimilate in this quick purview. So what are the computational issues? First of all, nanocomputing elements in the future, and I think all of us can see that this is the direction in which we're going. Performance, power usage in the area of digital computational elements are really dependent on the processes for building the chips. And overall, the state of current technology, the state of the art today is 45 nanometer technologies. Predicted capabilities in 5 years are 22 nanometer technologies. And people that read science saw the article last week, actually out of the University of Pittsburgh, that demonstrates how you can build 2 nanometer technologies probably within the next 10 years. So what we're talking about is extremely feasible. But the current question is, because we're looking at trying to do this in an evolutionary way, what amount of circuitry can fit into 1 cubic millimeter today and in the next 5 years? And what computation rate can be sustained with 1 milliwatt of power today and in the next 5 years, and then realizing that the technology is going to continue to evolve. So this is our estimate of what the current capabilities are today and in the next 5 years. And as you can see, 45 nanometer technology, we're talking about 50 megabits of storage basically on that order of magnitude. 22 nanometer technology, we're getting up to a gigabit. This is realizable. This isn't rocket science. This is what electrical engineering, computer engineering departments can do today and are working on doing in the next 5 years. The number of millions of operations per milliwatt of power, again, we're talking about for application-specific integrated circuits, 800 million operations per milliwatt of power with the 45 nanometer technology. With the 22 nanometer technology, we're up to 32,000 million operations per second. For application-specific chips, so these are chips designed specifically for the purpose. For a general purpose CPU, okay, your desktop Dell machine basically, which can do everything, you can postulate that in 2014, that chip, which will occupy a cubic millimeter and use 1 milliwatt of power, will be doing 800,000 operations per second. That's a pretty phenomenal number of operations. From my perspective, I have to tell you, the first digital computer I used was a Bell G15. Most of you have not heard of that, I'm sure, and you're lucky. It took you a whole day to add 2 numbers together. So to me, this is, when we're talking about where are we going, it's extremely realizable what we're talking about. So computational, let's see, did I go? Computational considerations, architecture, again, customized versus general purpose designs. That's a big question. That is one of the issues we're studying. Domain-specific architecture, namely you want to think about the architecture, go back to the block diagram in terms of functional blocks. You want to try to incorporate as much of the things into these blocks. Custom hardware accelerator modules, you can see you can build these very small, very low energy, and runtime dynamic reconfigurability. This is important when you think about implanting devices into the brain where you don't want to have to go back in unless it's absolutely necessary. You want the machines to be able to reconfigure themselves, adapt to the changing environment, the plasticity of the brain, all these, and the changes in the pathology of the brain. The VLSI implementation, specialized low-power techniques. You can see we're getting down lower and lower into what you can do with less power. Trans-threshold circuits. This is an idea in circuit design, which part of the time you run at some very low power level, some of the time the power level increases as the demand increases. And sloppy logic, sloppy arithmetic. We think about, we have to compute things in a very precise way. That happens to be a function of the way we think about the number system. But the brain doesn't have a calculus like what we're used to using. It's very sloppy, and we think we can build into the circuitry sloppy operations, namely operations which more mimic what the brain does. It doesn't do things precisely. So I want to go on now, and I just want to talk about approaches to other parts of the issues, because these are really big. Communications. Today the tool which is used for communications with implanted devices in the brain are either running wires through the skull, again referring to my friends at Medtronics. The second biggest failure in the DBS stimulators are the wires break, and so you'd like to do away with that, or RF communication. RF communication is not a good tool for communicating into the skull. So one of the things we think a lot about in our group is biomimetics. Oh, I'm almost out of time already. Haven't even got into the talk yet. Is biomimetics. So the body, it turns out, is a natural communication channel. EKG, if you think about it, this flow of information. We've developed this concept of volume communication, namely using the natural flow of information within the body to communicate. This works extremely effectively. There's a lot of information packed on this slide. Again, it'll be out on the website. And we've demonstrated it in implanted experiments in the pig. Second major question is energy thin film power transfer. Power transfer RF doesn't work. There was a very interesting paper out of MIT about 2 years ago. They called the subject of it was witricity, which is using focused magnetic beams, focused magnetic fields to transmit energy. This demonstrates an experiment within our laboratory. There's some text on this. Let's see if we can get it to come up. No, the text isn't coming up on these two things, but I will. Won't go back. So anyway, let me just take 2 seconds to tell you about the magnetic field thing. You can transmit very efficiently using magnetic field coupling, which is different than RF coupling, both information and power. And the efficiencies we've gotten in the laboratory, both in vitro and in vivo experiments, is on the order of 65%. We believe, and we're designing smaller and smaller coils, that this will be a very efficient way for transmitting energy to implantable devices as opposed to the RF techniques, which have a lot of problems. Second thing we've been looking at is, can you build power cells which utilize the natural metabolic processes occurring within the body? So there's a huge amount of electronic transfer occurring as we're all obviously aware of, within the mitochondria in the body. The answer to that question is yes. And we have done a lot of experiments, in this case using human neutrophils in vitro only so far, to demonstrate that we can capture sufficient energy from the white cells in the body to drive implantable devices once the power requirements get down to where we think they will be in the next 5 to 10 years. So that technology will be available. Algorithms, again, I want to just touch on this because this is a very important part of the whole problem. You're going to be able to acquire the data. You got to do something with it. Of course, that's the signal processing area. We're in the process of rethinking algorithms so that we can reduce the power requirements to do the computations required. The algorithms also have to take into account the plasticity of the brain. And there's 2 parts to that. One is neuronal signals themselves are inherently non-stationary. The other part of it is that the brain itself, the brain function, varies dynamically over space and time. That's one of the things that will be taken advantage of in the therapeutic applications of technology of this type. The algorithms must be flexibly parameterized. There's got to be trade-offs between graceful degradation, requirements for accuracy, power, and performance metrics. You're all used to thinking about computing in a fast Fourier transform. That won't work anymore if you want to do something. You've got to come up and redevelop it. And the algorithms must be co-optimized with the design of the processors. Namely, we can't say we're going to build a processor and build it independently of how we're going to do the calculation. So these two things have to play together against each other. The brain interfaces, different types of signal acquisition. To us, this is the major issue at this point. The analog to digital converters, digital to analog converters have to be integrated into the circuitry. We have to think about different ways of acquiring data. Most people are aware of the Nyquist sampling theorem. That's not going to hold. We have to be very efficient in how you acquire data, no matter what the data is. There's a lot of research going on in something called sparse data sampling methods, and we've been investigating that in our laboratory. Another approach is looking at amplitude quantization rather than time quantization. Again, using both of those, you can decrease the amount of data you have to acquire to make decisions on the data, and that's extremely important. We've touched a little bit on communication. Signal conditioning is making sure you have good data. Nanoscale technology is what we're talking about. But again, most people think about it with respect to the digital world. It also applies to the analog world. There is currently a lot of work available for development in this field, which we're going to apply to the analog devices. And then the whole question of how does hybrid calculations fit in? Can we take the analog and digital world and more intimately merge them? And I've got to stop. Thermal management, big problem. Again, this will be out on the website. I touched on it briefly. You can't let the temperature raise more than a degree, and our goal is to have it raise a lot less than that. Reliability and security, communications, you're worried about people being able to look at information, and of course that's all over the internet today, but this has to be secure. Enough said about that. Packaging, low profile, the first prototype will be less than a cubic millimeter. It has to be able to move in the brain. It'd be a set of stacked chips, as I referred to it. Let me just quickly take 2 seconds on this. Hopefully you won't throw anything at me. This, again, is an extension. This kind of shows you the two prototypic systems we're looking at working at currently. The one is the suppression of epileptic activity. Our initial experiments on that front with this kind of device will be in an animal model, penicillin model of epilepsy in a rat, which is a multifocal epileptic type of seizure that we want to control. The other application that we're looking at is the application of the brain-computer interface, namely functional electrical stimulation. I think in terms of how you think about this theoretically, the epilepsy kind of problem falls into this area of neuromodulation that was referenced in the first talk. The movement disorders, can you drive a movement device, falls into the area of control. So there's kind of a theoretical framework. This technology will happen. We're very close. And so the discussion, to accomplish these objectives, you have to rethink the entire systems design stack from application algorithms to implementation substrate. You've got to think about it as a whole. This device, when it's built, and we plan to do it in an evolutionary style, we have plans for the first 2 cycles through the process, will be the first brain implantable device to demonstrate significant computational resources within the implant itself. The traditional thing is you run wires out of the brain and you hook it up to your local supercomputer. And we believe the dramatic increase in computational capacity of the type of design that we're talking about here will be a disruptive technology, namely it will cause a fundamental shift in both basic and clinical neurosciences, both in terms of how we can study functioning within the brain and how we can help patients who have diseases that can be treated using this kind of information. So, thanks.
Dr. Sclabassi, that was a fantastic presentation and exactly on point with our session topic of telemanagement of very small devices. Great lead into our keynote speakers both today and tomorrow, Kevin Warwick, who has implantable devices. We have 10 minutes now for any questions and answers directed to Dr. Sclabassi. Please approach the microphone and kindly introduce yourself and if you feel comfortable, your affiliation.
I'm Sri Sridhar from Northeastern University. Excuse me. I'd like to hear a little bit more about your experiments you mentioned on using magnetic fields to couple energy to the devices. And I also let me throw out a broader question to you and to others. As we think about communicating with essentially implants of various kinds, whether they're going to be intelligent and functional like the brain implants, or even relatively passive implants. What are the ways of, it seems to me that we're almost driven to using low frequency coupling of some kind, because as you go higher and higher in frequency, for instance at RF, microwave, and higher frequencies, you're going to couple energy to the surroundings, which is really a severe problem in an environment such as the human body.
Great questions, actually. Those are worth the whole conference in themselves. Let me try to peel through the onion of those in a systematic way, because there's things we've thought a lot about. First of all, let's start with the communication problem. The approach that we really like for communication is the volume conduction approach that I referred to. I had the one slide. Unfortunately, the text on that slide didn't come up. But the core idea behind that approach is biomimetics. Namely, we realized that when you started to think about the EKG, the heart beats, the ions flow, and there's information transmitted. Why couldn't you use that same kind of approach to transmit information? On the slide I presented, I didn't get a chance to go through it, but there was a particular design to an antenna. We call it the X antenna. Now, it allows you to inject current into the surrounding tissue, which behaves in exactly the same way as the normal ionic flow within the body does. The bandwidth that you can acquire using this technology currently that we've gotten in pig experiments is on the order of 1 megabit per second. So that's quite a bit of information. Now, you can design that kind of device using various multiplexing schemes so that you can use that within the body and to communicate to the outside of the body. And the actual energy associated with the transmission of that information is extremely low. It doesn't appear to have, at least on the experiments we've done so far, have a detrimental effect. But energy is a big issue. Energy, has its thermal effects and everything else. So you have to be really aware of that. But we believe we're going to end up focusing on that as the primary communication tool. And we've published about 10 papers on that field and different things, and I can, if somebody is interested in them, and if you send me an email, I can send you the papers. On the question of the magnetic providing of energy, it turns out that, this was and I have to apologize, I'm blocking on the names of the authors. I should know them like the names of my sons at this point, but the paper that we got excited about was published about 2 years ago. It was out of the physics department at MIT. And they showed, it to us at that time was a very exciting experiment, which today turns out to be a very crude experiment, that you could use focused magnetic fields to transmit energy. And they were proposing that you would have this device sitting in the corner of a room like this, and everybody could drawing energy off of it to run their laptops and things. So we started to play with that idea, with the idea that could you use this to provide energy to implanted devices? And what we have done now at this point is we have designed about on the order of 20 different magnetic coils. And in the particular figure I had associated with that comment, what was being shown there was that, I don't know if you remember that figure, but there was a transmitter on top of the table, and then there were a series of coils going up and making a right turn, and there were some lights illuminated at 3 different points along that path. Well, the point of that figure was that you could steer this magnetic field to make a right turn and illuminate something at a distance. And we've designed a bunch of different coils that do this. Now, the coil designs are very different than what is used in RF coils. There's a magnetic coil. There's also embedded capacitors. The electric field gets locked up within the capacitive structure, and the magnetic field is what is actually transferred. As I said, the energy efficiencies we've measured so far have been on the order of about 65%. And we have coils all the way down to less than a centimeter in diameter at this point that exhibit these same properties. So we think that is potentially a powerful tool, both for energy and for communication, because you can force these coils to resonate simultaneously at multiple frequencies. So you could use one frequency of resonation to transmit power and 4 or 5 other frequencies of resonation to transmit information. So how that's going to play out against the volume conduction and all that, we don't have the answer to that yet, but it clearly works.
Okay, thanks. We have, thanks, Dr. Sclabassi. We have two last questions at the microphone, and Dr. Blumberg has one question after those two. So why don't we give a constrained answer to each of these 3 questions, and then in the breakout session, there'll be, we've planned every 2 hours, there's like a half-hour, breakout. There'll be time to pin you for more detailed answers. Next question, please.
I'm Eli Greenbaum at Oak Ridge National Lab. Thanks for the nice talk. So I think you may have answered this question but in your presentation, but I'd like to ask it again. You mentioned milliwatt power of transmission wirelessly. What is actually receiving that power, and is there a geometric relationship between the size of the object that's receiving the power and the amount of power that you want to transmit?
Well, there was what I mentioned was the constraint on the computational devices was the utilization of 1 milliwatt of power. That's our current constraint that we're designing to. So that's the power that we're envisioning being utilized within an implanted element in this distributed network. So it's not the transmitted power to the outside. Now, the energy that we would have to provide to that device is a milliwatt, and that would come either through the magnetic field approach or through the white cell approach, scavenging electrons through from the metabolic pathway. So the energy that would be actually transmitted to transmit information coming out of the system would depend on how that information was going to be utilized. And the way we envision this working in both of the applications we're working on now, you would be able to extract information out of the system to the outside environment, but most of the information would stay within the system. You could conceive of it as a closed-loop system. So the milliwatt power constraint was our current energy budget for the computational elements. Now, I'd like to make one quick comment on that, if I could.
Sure, because we have in session 2, we have some papers specifically on the topic of, but please.
Yeah, we believe that in 20 years, the architecture size will be 2 nanometers for devices. The corollary of that is where today we're talking about milliamp of current draw, that we'll be talking about femtoamps of current draw, namely 1,000 electrons moving will produce the information transfer within these devices. So the power budget will drop even considerably less than that.
Yes, size matters inversely. Next question,
Thank you.
please.
Jay Yadav, CardioMEMS. Dr. Sclabassi has a very interesting talk. The author on that paper, by the way, is Kurs, K-U-R-S, from Science, for those of you who want to look it up. I won't digress on that topic because we have looked at that carefully and we're a little less enthusiastic than you are, but I'd love to talk to you later about some of your research in power transfer. Going back to the brain, there have been a couple of companies over the last few years that have tried to do some of the things that you're talking about. North Star Therapeutics for stroke rehabilitation, and NeuroPace for epilepsy prevention. And they've met with limited success so far. Could you perhaps clarify from your vantage point what the issues have been in trying to commercialize these technologies?
Yeah, well, first of all, I think at this point, we're not looking at trying to commercialize this. I think commercialization for this would be 20 to 25 years out from today. So I think that's important. This is a research project at this point, which has 4 collaborating institutions: Computational Diagnostics, which is a company; Carnegie Mellon University, which is University of Pittsburgh; and Allegheny Singer. It's a team of neuroscientists, electrical engineers, computer engineers, neurosurgeons, materials people. There's about 20 people in the team. So we're not looking today at a commercial product. But we believe that this will be a commercial product in 20 to 25 years. So where have the companies gone now? So of course, actually, Medtronic, who's represented here, and we had a great opening talk from Medtronic, has been a key player in deep brain stimulation for control of movement disorders. Very successful. A lot of problems also. North Star has attempted, people that aren't familiar with them, they attempted to treat strokes through cortical stimulation. The core idea being that they would produce plasticity within the cerebral cortex. They didn't meet their primary goals in a clinical trial. And the reasons probably are because they were trying to do something with a hammer. They're trying to hit a nail with a hammer when they were actually trying to turn a screw. It'd be the way to think about it. So I think they picked the wrong target. There was another company, Cyberkinetics, I believe, out of Providence. They attempted to build implanted stimulators. Again, very crude, just the stimulator part, running wires out or RF communication out. Not thinking about it from the total system perspective. The two areas we've picked for the primary application experiments, at least through the first 2 circles of the evolutionary cycle, are ones in which we know that there is data which supports the treatment. Namely, movement disorders, we know that if you stimulate the subthalamic nucleus, you can suppress the movement disorders related to Parkinson's disease. We know that if you stimulate the anterior thalamic nucleus, you can suppress seizure activity, and both of these in the human. We're not going to do the experiments in the human in the next 5 years. We'll be doing them in animal models, but we know that those therapeutic interventions work. So what we're essentially doing is putting a control loop around them and driving down the computational elements. So I think the fundamental conceptual approach to attacking the problem is a little different. It's a great question.
Thank you. Dr. Blumberg?
Just a brief comment, and maybe possibly a premature one. Has there been much thought on the legal consequences of having a implantable device which would record events, for example, that precipitated an accident or an intent for violence or murder or something? That's again, you've just pointed out it's an experimental problem now, but I'm sure you've given some thought to this.
Yeah, that's actually a subject for a whole week conference. The legal and the ethical questions are very deep in this area, and people that pay attention to the popular press, you see these articles all the time, particularly out of Carnegie Mellon, I have to say. So, we now understand how the brain works, and we can see how people think and formulate thoughts, and this is all based on fMRI data, and none of it really makes any sense. But the reality is there are deep legal and ethical questions here that need to be thought through. And we've thought about it a little bit, had discussions with lawyer friends, had discussions within our own group about the legal, ethical, philosophical issues of implanting devices into the brain, which allow you to start to sense what's going to start to happen, even though behaviorally you don't see it yet, and attempting to control that. And you can get into all kinds of conceptual paradigms which cause a lot of difficulty in how you think about these things. That's a great question. I'd love to talk about it at length.
Thank you very much, Dr. Sclabassi. By the way, thank you very much for the individuals who have come up to the microphone to ask questions. Those have been fantastic questions, and it's precisely why we've tried to balance the program to have a 2/3 presentation and 1/3 interactive Q&A, because we really tease out a lot more information this way. And I apologize that all the questions can't be answered within those 10-minute blocks, but again, we have frequent breaks. And as is the case with so many workshops, I think the greatest amount of insight occurs in the hallways.